My job at the University of Illinois is writing molecular visualization software, so I've had a long experience with writing OpenGL programs and things like this, and over many years that evolved into programmable shading, and so I started using programmable shading to improve our molecular visualization software, and that sort of was a precursor to what is now happening with GPU computing. In 2007, Nvidia's David Kirk came to University of Illinois and jointly taught a course with Professor Wenmei Wu, and myself and several of my colleagues sat in on this course and basically learned about what was happening in the computing side of GPUs, and we started experimenting with using these GPUs for some of our scientific calculations. And that led to some early experimentation, which was very successful. And then in the year and a half since then, we've continued to explore the use of GPUs for scientific computing and for visualization, doing non-graphical calculations, primarily with CUDA. So that's been our hot area of research for us. Before 2007, to get involved in using GPUs for scientific computing involved using the graphics programming interfaces, which are unfamiliar to anybody who isn't a hardcore graphics programmer. And so I would say, the way things stand now with CUDA and with things like OpenCL coming, it is much easier for somebody who is just a straight C programmer to take an algorithm that they are already familiar with and implement it in a data parallel manner on a GPU. And I would say that it's getting easier as time goes on, as the hardware gets more flexible and the performance intricacies are easier to understand in the newer models. All these things are getting easier as time goes on. Simple algorithms that ramp up from an early experimental version to something that is production ready can be very fast, actually. There are a lot of computational kernels that are very memory bandwidth intensive, or they're extremely floating point intensive. Even though they may have very simple memory access patterns, those are usually very easy to ramp up to production quality and flexibility. I would say where you have more of a challenge is when you have irregular data structures, when you have highly branched search algorithms, things like this, or irregular data access patterns. Those are things that are a little more complex and require a lot more care and planning in writing a GPU kernel, and those tend to take longer to perfect and debug and so on the GPU than they would on a CPU. But I would say, it can be a matter of hours or days, for the simple ones, and maybe it takes a few weeks to really make a complex kernel run well. At the University of Illinois, they've taught this CUDA course twice, and a lot of the students pick it up very rapidly. So it's not tremendously difficult to understand the key concepts. Getting the peak performance is a little more challenging, but that's not unusual. That's the same thing if you have to write SSE code and you are counting instruction cycles and things like this, trying to get the machine to perform at 99% of its peak. That's challenging no matter what the target hardware is. So that's, there's certainly more effort involved if you want to really make the GPU run at the large fraction of its peak performance. But the thing that's fun about GPUs is even with the simple-minded implementation of some of these algorithms, a person can get a significant speed up even before they've really addressed these performance intricacies. So that makes it a lot of fun to do.